Our next distinguished presenter is Professor K.L. Ramakumar. I would like to invite him for his presentation on the chemistry at the front and back end of the thorium fuel cycle. Professor K.L. Ramakumar is a distinguished scientist and is a director of the radiochemistry and isotope group coordinating research and development activities of 6 divisions catering to both front-end and back-end nuclear fuel cycles, radiation processing, isotope. Okay, thank you. Professor, the floor is yours.
Thank you. Namaskar, and a very good afternoon to all of you. I am going to speak to you about the role of chemistry in the front end and back end of thorium fuel cycle. And this work, I know, is an involved one, and I acknowledge in the beginning itself the contributions of my colleagues, particularly Dr. S.K. Mukherjee, Dr. S. Parida, Dr. S. Kannan, D.S. Tomar, Goswami, and other colleagues in the group who probably carried out much of this work. Because of their involvement, I am here in front of you to speak about the role of chemistry in the front and back end of thorium fuel cycle. Well, this is an introductory slide only to reiterate what has already been told about the long-term sustainability and future expansion of the nuclear power program in India. Of course, because of our limited uranium resources, to a great extent on the large-scale utilization of thorium resources for breeding uranium-233, and of course recycling the same in the self-sustaining thorium-233 closed fuel cycle in appropriate reactor systems. And the paucity of the literature on the various data that are supposed to be required to realize the dream of development of thorium-based fuels necessitated chemistry-related research and development activities. And in our group, we have taken many initiatives in this direction, particularly the research and development pertaining to the chemistry aspects of thorium fuel cycle, which have been initiated. In this connection, I would like to concentrate only on two aspects of the research and development that has been carried out in the field of advanced heavy water reactor systems. And of course, we have initiated another research program on molten salt reactors. The chemistry really plays a very divergent role. This is only to show you some aspects of the chemistry-related research programs that are possible in thorium fuel cycle of advanced heavy water reactor systems, starting from fuel fabrication processes, dissolution, analytical methods for chemical quality control, of course understanding physicochemical properties, chemical interactions in the reactor operating conditions, of course the simulate and reprocessing, and of course waste immobilization. And I can have another chart for the molten salt reactor systems. Again, different areas where chemistry plays a very significant and inevitable role to realize the development of the molten salt reactor systems. What I am going to present today does not really cover all these aspects. Only the aspects which the group has undertaken over these years, I am going to give you glimpses of those activities. In fact, somewhere in 1999, early parts of 90s, a task force was formed to understand the behavior of thorium-based reactor systems. And our colleagues, Mr. S.A. Bharadwaj and Dasarathi Das, they have compiled the different research activities along with the literature available, and Springer has published this particular compendium on Thorium-based nuclear fuels, thermophysical and thermodynamic properties, fabrication, reprocessing, and waste management. And it deals with a comprehensive account of chemistry-related aspects of Thorium-based nuclear fuels. And there are a number of groups which have taken part in this gigantic exercise. And the experts have come out with the individual chapters which probably would really throw a light about the whole gamut of the chemistry-related Thorium-based nuclear fuels. What I am going to do is only to take a brief of the activities. One such is development of sol gel process for AHWR field fabrication, and I am happy that my previous speaker, Mr. Ramakumar, did deal with these aspects, but I am not going to give you the full details. I am going to tell exactly how we were able to use this impregnation technique to realize the thorium-uranium based. So presence of appreciable amounts of uranium-232 in the advanced water reactor fuels. In fact, this uranium-232 content depends on the burn-up, varies anywhere between a few ppm to 500 ppm. And of course, that depends on the flux characteristics and exposure duration. And sol gel, of course, is one of the most attractive techniques in this direction because we can do away with the powder handling. And among these three methods, sol gel, microsphere pelletization, vibrosol route, and impregnation technique, I am going to highlight the advantage of only the impregnation technique, which Arun Kumar so nicely elucidated. This is because we were able to really get the preparation of porous thorium. The first and foremost requirement is to go for the preparation of porous thorium oxide microspheres. Then we go in for vacuum impregnation of uranyl nitrate solution, and after heat treatment we go for pelletization and sintering. Of course, the advantage is I need not have a complete shielding facilities. I can go only for the minimum manual handling and of course radiation shielding if fresh thorium is used. And it can be really automated and remotized. This is the flow sheet we normally follow. First we make the thorium oxide pellets, and then we go for the impregnation technique with uranyl nitrate, and ultimately we sinter at 1350 degrees Celsius for 4 hours in air, and of course reduction in nitrogen hydrogen atmosphere at 600 degrees Celsius. This is the walk-in glove fume hood facility which is being operated to make this thorium pellets, and then of course later on we go in for glow box for uranium shell. As of now we do only simulated, and the process has been optimized for uniform and homogenization loading of uranium microspheres. We have optimized many of the parameters as indicated here, namely the concentration of uranyl nitrate solution, vacuum level of the fuels, and time of impregnation, and of course morphology of thorium oxide microspheres. Using this, the optimized parameters, a flow sheet has been really standardized, and the results that are obtained are shown in the form of SEM photographs. We were able to go in for 3 to 5% of impregnation with 8% loading of uranium consistently on thorium oxide microspheres, and we do get a very good quality of sintered thorium pellets. So pellets of density between 94 to 96%. And of course, the elemental mapping did result and showed that it's really homogeneous of uranium in the microspheres as well as in the pellets for all the samples that has been prepared so far. And of course, this is only to show you the quality of the microspheres and thorium oxide pellets, and of course thorium uranium oxide pellets which have been obtained using this impregnation technique. Then I proceed to the dissolution behavior. There was some question raised into the previous speaker whether we couldn't do away with utilization of hydrogen fluoride. I thought I would, in addition to what Mr. Vattal has indicated, I can, instead of fluoride, they could use chloride. But we have completely used a different technology, different method, a simple and fast method for the dissolution of sintered thorium oxide and uranium thorium oxide, sintered between 1600 to 1700 degrees Celsius, which has got 94% theoretical density, by using solid solution route, by reacting oxides with ammonium sulfate at 360 degrees Celsius. It is a solid reaction, solid reaction. It does not go in for that type of nitric acid, hydrogen fluoride. What chemistry is only it reacts with oxides about 250 degrees Celsius, ammonium sulfate, to form their respective sulfate compounds, which are readily soluble in dilute nitric acid. And of course, advantage, I need not to reiterate, of this reaction that even the excess of ammonium sulfate, even if it is used, is more than required for with respect to the stoichiometric amount which we have calculated. It decomposes into volatile gases, and that does not leave any residue. We were able to dissolve more than 99% of thorium and uranium brought into solution in the form of soluble form in dilute nitric acid, when a mixture of thorium oxide or of course our thorium uranium ox and 6 moles of ammonium sulfate were isothermally heated at 365 degrees Celsius for 8 hours. So this is one of the techniques that we could really use. The only precaution that we have to take is to see that the particle size of thorium oxide or thorium uranium oxide should be more or less same in the region of ammonium sulfate we are using it, so we need pulverization. Then coming back to the analytical methods that we have developed for the chemical quality control, knowing how difficult it is to dissolve thorium oxide or thorium uranium oxide, the emphasis has been given with respect to development of analytical methodology to the extent possible use only the solid materials for the chemical quality control. So the first and foremost what we require is the availability of reference materials for the chemical realization. In this direction, this group long ago did prepare copious amounts of thorium oxide and thorium uranium oxide reference materials with known impurity contents added, and these have been certified through a round-robin inter-laboratory intercomparison exercise, wherein 13 DIA laboratories participated, and 3 such reference materials have been prepared and certified for 20 elements. And in order to achieve this goal, different analytical techniques have been employed, and a rigorous statistical treatment has been applied before giving the certificate of these trace constituents present in these 3 so-called reference materials. The techniques that have been employed are ICP-AES, ICP-MS, chromatography, X-ray fluorescence, spectrophotometry, and DCR chemical spectroscopy. And in addition to that, recently we did use even laser-induced breakdown spectrometry to revalidate the concentration of some of these trace elements. And the flow sheet that has been followed, I don't want to go into details. This is the flow sheet we have followed to prepare these reference materials, and these are the certified values for these 20 elements, and these are being used routinely for our chemical quality control measurements. And I mentioned there is one laser-induced breakdown spectroscopy is a solid analysis technique which has been now being used routinely in our division to carry out a number of analytical measurements. Some of them I have indicated here: elemental characterization in power reactor, Thoria reprocessing facility for phased glass characterization, and of course temporal study of plasma parameters, quantitative study of uranium thoria oxide, and concentration dynamic range between 1 to 25 weight%. And of course metallic impurity studied in thorium oxide. This is where that reference materials really were used. and of course that quantification for boron lithium in these materials. This is only a glimpses of some of those by applying partial least square regression calibration approach, we were able to really carry out a different analysis of elements starting from silicon, boron, sodium, barium, etc., where we were able to use a multivariate statistical treatment to really arrive at the concentrations despite having lot of noise and interference from some other elements. This is where the literature effect, and this table gives you the FCD and RST that we were able to realize in some of these elements that have been determined using laser-induced breakdown spectroscopy. It has got a very vast potential in chemical quality control. And of course, this is another glimpses of the quantification of uranium thorium oxide in the concentration dynamic range of 1 to 25.8%, and it is self-explanatory. I need not to go deep into the details how the treatment, etc., the statistical model have been applied to arrive at this concentration. And the lower table gives the metallic impurity concentrations with respect to some of the standards that we have employed. And we also do use the high performance liquid chromatography basically to standardize, to develop a method for the determination of burn up, and then there we have used 139 lanthanum, not the neodymium 148, which is the normally used isotope in uranium plutonia based field materials. For thorium plutonium, we have identified lanthanum 139 as the ideal burn up monitor because the fission yields between uranium 233 and uranium 235 are more or less same, and the developed technique could comfortably used for determination of the total separation of total rare earths as well as the lanthanum 139, and the conditions that have been optimized are given here so that people could make use of this developed technology to separate lanthanum for the burn-up determination. And another important technique that we have developed is the total reflection X-ray fluorescent technique for thorium-based fields. And this is a microanalytical technique, very small amounts, 2 to 10 microliters or less, and the resulting in a very minimum amount of waste that is generated, and of course very simple quantification. What we need is only a single internal standard, and I can go for multi-element analysis technique right for carbon to uranium, including metals and non-metals. And of course for major element determinations, we don't require, of course, no sample preparation involved, and of course it is a very simply, we just crash the pellet and put that wafer there under the TXRF, we were able to realize the techniques. And of course this is how we have used and calibrated the technique for trace elements in the detection of thorium oxide. This is another important TXR, the technology, the technique we have employed to revalidate our reference materials, which I mentioned to you earlier. And we also used a micro SRF, synchronous radiation, to identify the homogeneity or distribution of uranium and thorium in thorium oxide 4% uranium oxide pellets, where these were prepared by powder metallurgical compaction route, that is the top one, and of course the coated agglomeration. We could really see that CAP really gives advantage of non-destructive, vast dissolution, and no sample preparation. So we feel CAP is a better alternate technique than powder agglomerated. And we also compare for the non-metallic determination of chlorine by using two independent techniques, namely the TXRF and ion chromatography, which is being very routinely used to determine the chloride concentration, of course all halides, and we extended this applicability of TXRF to non-metallic impurities, including chlorine. And in addition to carry out this chemistry-related aspects of it, we would also have the mandate to develop, to construct the phase diagrams and thermophysical properties of this thoria based. And these are the topics that we were involved in: thermal expansion studies, thermal conductivity, fuel fission product, chemical interactions, oxygen transport in the fuel matrix, thermodynamic assessment of HWR fuel systems, fission gas and volatile fission product transport. I would like to mention that probably my subsequent speaker, Dr. Jagtap, may probably have something to touch upon these things. So I am not going to take your valuable time to have this type of presentation. I'm going to bring to you only what has been done in our group using the Thermocal software package to compute the phase diagrams for thorium uranium oxide systems and thorium and plutonium oxide systems. And of course, we also go in for the computation of oxygen partial pressures for hypo and hyperstoichiometric. And these are the things which are really needed before we really take a decision to go ahead with respect to the irradiation studies. And a simulation study, SimFiel has been prepared only with respect to these studies. And then this has given a very valuable data for us to take a further decision as to how to go about it. This is the task force that has been talking about, a report on the task force on thermodynamic and transport properties of thorium-related based fuels, which has been published way back in 1999, and a part of it has already been referred to in that compendium which has been published by Springer, and only two of those things in terms of thermal conductivity of thorium oxide based fuels, we say it is better than uranium oxide fuel. And then of course, the thorium lanthanum oxide system data suggests that with increase in burn-up, the thermal conductivity of AHWR fuel decreases. This is something which probably would be taken as an input while taking a decision with respect to the AHWR fuels. Similarly, for the comparison of apparent diffusivity of iodine and tellurium in AHWR, SimFiel, that has been really synthesized, and then we published this with respect to iodine and thorium diffusivity in AHWR fuel that indicates how tellurium and iodine in comparison to each other, it is indicated in this graph. And of course, oxygen diffusion also has been studied, and then it's written that diffusion coefficient in HWR fuel is far less than that we normally come across in uranium oxide. It is almost 10 to the power minus times less. So this is how the data that could be produced were able to use in designing the fuel. So conclusions to the HWR fuel has less thermal diffusion and better thermal transport properties. I hope Vijayan Saab would agree with my observation in chemistry related points, because he is the architect for HWR. There should not be discussion. And HWR fuel is found to have a poor buffering ability and transport properties for oxygen. Molybdenum oxidation kinetics controls the oxygen potential, and I need not to read, it is there already. Intragrain diffusion rate species is lower in thorium as compared to uranium. All these facts have been taken into consideration before designing the fabricating the fuel for HWR. I just come to the reprocessing of thorium-based spent nuclear fuel. This is a very small contribution from our group. Of course, Vattal's group has been really actively pursuing this activity. We were able to show that amides, branched amides, have got a potential alternative capability to TBP in the ThEC process. Particularly the dialkyl aliphatic amides, we were able to show that they have got better extraction behavior for metal ions. Radiolytic and chemical degradation products are innocuous because they could be washed out by water, leading to simplified solvent treatment, and completely incinerable, leading to the reduced volume of secondary waste as compared to that of TBP. These interesting features of amides have led to explore the applicability of these amides alternative to TBP in thorium. This is a simple amide process which has been developed. Of course, we had the pleasure of having collaboration with the nuclear recycle group in extending these studies further, and we were able to show that DHOA, di-N dihexyl octanamide, was identified as a promising alternative to TBP for proposed HWR spent fuel reprocessing, and this is the typical flow sheet which we thought we would be able to use it. And then I'll come to
we have
briefly.
Very limited time for the questions.
So, two more minutes. to go to the R&D of molten salt systems. This way back in 1970s when Oak Ridge was really actively pursuing this, we also wanted to contribute, and in that way in 1970s we studied the solubility of plutonium fluoride in many salt systems, and then we were able to fabricate some of the apparatus that was required, and then we were able to show that solubility variation of lithium fluoride, barium fluoride, thorium fluoride, tetrafluoride in binary salt mixtures at different compositions. That was stopped afterwards. Obviously, the interest was dwindled, and subsequently now we are able to take up this particular we have established a completely new facility for the purification of fluoride salts, and of course now it has been already used with respect to the preparation of eutectic of thorium fluoride and lithium fluoride, which was actually supplied by RED, and we were able to prepare a eutectic mixture and study its properties, and reported melting point is 560, and we were able to determine within 564 plus minus 2 degrees Celsius, and XRD analysis confirmed that eutectic has indeed been formed. Probably we will be sharing this information to the reactor engineering division shortly. This just 1 week ago we were able to demonstrate this particular thing. And of course, this is another the thermodynamic data for oxyfluorides. I think probably I would not really be in a position to go into deep into details because of lack of time. What we have developed is the oxygen partial pressure. We have to control in such a way that we would be able to get the formation of U2O2 and of course the HO2 oxyfluorides. This is what is required to, in summary, the various R&D programs that have been initiated in the group in PRC to investigate both back and front end of cycles and flow sheet of HWR field fabrication by impregnation technique has been really standardized and developed, and Thoria solid route has been identified for dissolution of thoria, which does not require in hydrogen fluoride, and of course CQC phase diagrams and facility for the molten salt preparation. We hope we'll be able to come out with more challenging research activities in molten salt applications. And thank you for your kind attention.
Thank you, Professor Ramakumar, for your nice presentation. Now we can have a couple of questions from the audience. Yes, sir.
I have a question about the ThEC15 analysis. The analysis was performed on solid samples.
Which analysis?
Phase.
The total X-ray fluorescence analysis.
Total reflection X-ray fluorescence. Yeah.
Yes.
No, we take a small, if it is a bulk sample, we take a swipe of it, and then that swipe is kept under the ThEC15, and then straight away we take it.
But it's a solid material, or it is dissolved?
Of course, we had that solution at the top of nitric acid, because it hardly any material that is present, so we do detect that.
And is it also applicable to the determination of fluorine? Because
yeah, we did all non-metallic impurities, we did, but that result I am not showing it here.
Because, so it's both applicable to chlorine as fluorine analysis?
Yeah, we're using ThEC15. We have not yet started that, but there is potential for using this technique for fluoride also.
And would the method also be applicable for ThEC15 analysis of uranium dioxide? Would it also be possible?
We did, yeah. We did.
So also on uranium dioxide? Yeah. Okay, thank you.
Thank you.
One more question we can have. Okay. There's a microphone.
Thank you very much for the presentation. The last few slides about the salt were promising for us. Do you have some plans or visions how to, or it will be based on demand of other departments? So do you have some plans what to measure next for the salts?
Continue.
If you have some future plans for
HWR, yeah.
For the salts measurements and
yeah. In fact, We believe in our group, the research is a continuous process, work in progress, and we also identify some research potential areas. And as of now, we were given the mandate, is there any way we can do away with beryllium, use of beryllium, and then see that whether we'll be able to identify the suitable salts because of toxic nature of beryllium. But we have to really, it is a challenging one, and we would like to really go further. And then maybe, you see, this is thorium fluoride, thorium fluoride and lithium fluoride is one such particular exercise in that direction. So we would like to really continue, and I understand that we do have a program for molten salt reactor research, and I am sure that my colleagues in engineering discipline would come out with many challenging chemistry related research activities, and we hope to contribute to realize this dream.
Thank you very much, Professor Ramakumar. On behalf of the organizing committee, I would like to present you this memo.